Hello everyone, thanks for watching this video. My name is Boqian. I'm glad to introduce our work TCB, Accelerating Transformer Inference Service with request concatenation. I have divided my presentation into 4 parts. In the first part, I will introduce the transformer models and NLP-related service system. Then, I will point out the problem in here and why we need to solve that. Transformer has shown great power in application related to natural language processing, thanks to its unique self-attention mechanism. There are many applications deployed on this model, like Google Translate, AI Girlfriend, Google Search. The right picture is the architecture of transformer. It has an encoder and a decoder. Both of them are designed on attention mechanism. You can find more detail in the paper. Attention is all you need. The NLP-related serving system, which usually resides in cloud, receives inference requests from end user and should make response with low latency. In the example, the requests are the sentence from users. The system will buff them into the request queue, and then they will be batched together by schedule module to feed into GPU. However, existing transformer inference methods are not efficient. Let's see what happens in here. For example, language translation service receive requests in the form of sentence, and obviously these sentences are with different lengths. A common optimization is to inference efficiency is to batch several requests, which are further described as multi-dimensional tensor that can be processed by GPUs with high efficiency. When batching, short requests need to be zero-padded so that they can align with long ones in the same batch, and the batch row length is fixed and shorter requests are padded with 0. This is the default batching schedule adopted by popular machine learning platforms. This token fulfilling it will waste GPU computing and memory resource. There are some related works about batch strategy. The first is the default setting. It has a fixed batch size and shorter requests need to be batched. To reduce overhead incurred by zero padding, turbo batching, which are adopted by turbo transformer, which reorders requests according to their length and batches the one of similar length. Such a length-aware batch scheme can significantly reduce pad 0, only if it is fed by a sufficient number of requests with similar length. However, the requests received by serving system could be quite different lengths, which makes the length-aware batching scheme cannot always play its full power. And the third is our proposal. We concatenating two requests together is the most flexible and is able to handle the request with arbitrary length distribution. A straightforward request concatenation may lead to wrong inference results, so we try to put the concurrent batching into the existing inference system, but we got the wrong results. So we need to modify the inference algorithm. Another issue of existing work is the lack of request scheduling policy. With tight integration with request batching scheme, request scheduling policy determines which requests should be served first, when batching scheme decides how they can be served. Request scheduling and batch have complex interaction, which unfortunately has not been well exploited by existing works. We deserve an algorithm that can fully exploit the potential capital of concatenation batching, when being aware of request deadline to guarantee a certain level of service quality. In the second part, I will introduce our system and some details about the schedule module and the inference energy. This is our system overview. It receives inference requests, usually in the form of sentence, from user applications and processes them using two core modules: a request schedule and a customer inference engine. Each request contains a sentence to be processed, associated with an arriving time and a desired response deadline. When GPU is idle, the schedule packs some received request into a batch and sends it to the inference engine. A request scheduling algorithm is designed to decide which requests should be batched together by jointly considering request concatenation, request deadline, and running speed of inference engine. The inference engine is responsible for running the transformer inference computation in GPUs. Therefore, we customize the self-attention computation process to guarantee inference correctness. And the inference engine is to address the challenge 1, and the request schedule is addressed to challenge 2. Is addressing to challenge 2. Self-attention is the most critical computation in the transformer inference. TCB customizes self-attention computation to guarantee correct inference results. Here is the 3 requests concatenated in the first batch row. Then, when they compute the self-attention, it will face a dilemma of the close attention in each request, like the red blocks. This will affect the inference results. So we designed a mask matrix for offsetting the infection of these blocks. The calculation result is equivalent to the inference of 3 requests separately. Called DAS is described as a function whose positive codes are shown here. This function is invoked at the beginning of each time slot. This function returns a batch of requests that are sent to GPU for inference in time slot. Note that requests that have arrived but been not scheduled by their deadline are included. The function will sort the requests by value firstly, and then it will divide the queue into 3 parts by the system parameters Q and K. The second part will resort it by deadline and fit into the one row of a batch. During inference, a batch, no matter with or without request concatenation, and its intermediate data are kept in GPU memory until inference results are generated. An important observation in our experiments is that the inference results of requests in a batch are generated at different times. So we split a whole batch to 3 slots in this picture. For each slot, it will finish earlier. So the straightforward idea to improve GPU memory efficiency is to remove the data of requests whose results are generated, instead of waiting the completion of whole batch inference. In such a way, the GPU memory clean overlaps with the inference process, bring additional performance improvement. Compared to pure request concatenation, the algorithm designed for slotted request concatenation is more challenging, because batch decisions are affected by slot size, which become a new optimization dimension. We designed a heuristical algorithm for slotted request concatenation, and here is the procedural code of algorithm. In the third part, I will introduce the experiment setting and the performance of our results. We test our code in the AWS instance P3.2x large, which has an NVIDIA Tesla V100 GPU, and we used a simple machine translate model, sequence-to-sequence encode-decode model, which from attention is all you need. In batch strategy, Our baseline is TNB, which is the transformer with level batching, and the TTB is the transformer with turbo batching. We also compare with 3 schedule algorithms: short job first, first come first served, deadline early first. We randomly generate requests with 3 to 100 tokens according to a normal distribution, and they arrive at a portion process. The batch size is set to 64 for TNB and TCB. We follow turbo transformer to use a dynamic programming method to determine the batch size for TTB, as shown in the picture in the top. System utility increases as a rising rate grows for all systems. The maximum performance gaps of our batch strategy with TNB and TTB are about 2.22 and 1.48 respectively. We then studied the system performance on the simple first-come, first-served schedule policy. This set of experiments animates the influence of our design schedule algorithm so that we can better show the benefits of request concatenation adopted by TCB's inference engine. We first set the variance of request length to 20 and show results in the left picture. Thanks to request concatenation, the maximum throughput of TCB is higher than TNB and TTB by 3.33 and 1.52. The maximum performance gaps between TCB and TCB increased to 1.72. To show the superiority of our proposed DAS algorithm, we equip TCB with 3 popular scheduling algorithms, like short job first, first come first served, and deadline early first. And we test on the different batch size, variance, and input length. The results on the different batch size are shown in Figure A. Note that we use the same TCB inference engine for all algorithms. The utility increases as the batch size grows for all algorithms because large batch size can accommodate more requests. DAS TCB outperforms others at all batch size. We then fix the batch size to 16 and study the effect of request length variance. As shown in Figure B, DAS TCB has obvious improvement in the utility compared with other schedule algorithms, which demonstrate that DAS TCB is aware of requests of variable length and makes better scheduling. We finally changed the batch low length. You also can see the input length, the parameter L, and show results of different scheduling algorithms in Figure C. DAS TCB has about 40% higher utility than SJF TCB, and more than others. All the results show our schedule algorithm has a better performance. Also, we test our overhead of schedule module in our system. The schedule module has a low overhead in the inference of a batch, but the overhead will be bigger when the request arriving rate is increasing. I will summarize the contribution of our work. TCB is an NLP-related inference system with the objectives of high throughput, high GPU utilization, and low latency. We designed a new batch strategy to reduce computation redundancy. Thanks to request concatenation, the maximum throughput of TCB is higher than TNB and TTB by 3.33 and 1.52. We also designed a new schedule algorithm to maximize the total utility of schedule requests and fully exploit the potential capacity of concat batching. DAS TCB has about 40% higher utility than SJF TCB and more than others. That's all. Thank you.